In this video, we are going to introduce the concept of multi-body modeling with some mechanics. Specifically, we will talk about what is sim mechanics, terminology used in sim mechanics and multi-body modeling such as solids, coordinate frames, and joints, and finally, how to visualize multi-body components. A simplified suspension system is used to explain the concepts of multi-body modeling using sim mechanics. The first question to answer is, what is sim mechanics? Sim mechanics extends Simulink and Simscape. Note that the discussion about the difference between Simulink and Simscape modeling approaches applies to Simulink and sim mechanics as well. Please refer to the Simscape introduction training video for more details regarding this difference. Sim mechanics provides the ability to easily model rigid body mechanical systems both in 2 and 3 dimensions, whereas Simscape models one-dimensional multi-domain systems. Sim mechanics can also be interfaced with Simscape. Please refer to the documentation link in the resources section to get more information about this. This introduction gives us an idea about what sim mechanics is capable of. Let's take a look at an example by switching to MATLAB. Here, we see the visualization of a suspension system. Let's simulate this model by clicking on the Run button here. We can see that the system is undergoing different types of force tests. We see the right and left wheel. We see the suspension arms. We also see the shock absorbers. We have some visualization for the instantaneous and the roll centers. We can change the views here. For example, I can click on the isometric view. I can click on the top view to see the different types of orientations for the model. Let's go back to the isometric view. I can also rotate the model here to look at custom views. Let's go back to the right view. This is the visualization of the model. The actual model itself is in the Simulink environment, as can be shown here. Let's go ahead and zoom in on some of these subsystems. We see the left and right wheel suspension subsystems. Let's double-click on one of these subsystems. Here we see the 2 arms, the shock absorber, and the wheel. Let's go back one level up by clicking on this breadcrumb here. We also see the test force subsystems exerting force on the wheels and the suspension systems. Having Simulink as the environment allows us to use subsystems to group together mechanical components in a hierarchical fashion. Let's go back to the visualization. As we can see, this model has several simplified components. These are built from within sim mechanics. The advantage of doing this is that we can easily parameterize the model and optimize design iterations automatically using MathWorks design optimization tools. We will see this later in another video where we will optimize suspension design parameters to meet certain performance goals. Apart from this, we can also import more complex parts from supported CAD platforms. For example, we could import the arm here as a CAD part from SolidWorks for dynamic simulations. Apart from individual parts, we can also import entire assemblies from supported CAD platforms. We will see this in another video as well. This introduction gives us an idea about what sim mechanics is capable of. Let's go back to the presentation for a bit. We saw an example model of a suspension system to demonstrate important sim mechanics capabilities such as modeling and visualizing 3D mechanical systems with multiple rigid bodies and taking advantage of Simulink environment to build reusable components. Now, let's take an example of a simpler mechanical system, model it with sim mechanics, and simulate it. We are going to model a single link pendulum. In our suspension model here, we will remove the shock absorber mechanism and the arm. We will also remove the wheel so that the arm can rotate about the z-axis. We can simplify this model even further by turning this link into a single brick-like body that acts like a pendulum. Before we start building this model, let's learn a few concepts and terminology that generally apply to a multi-body simulation. We can see that this system is comprised of a single brick-like shape. This shape is represented as a solid in multi-body simulation. To model the system, we will define how the pendulum moves with respect to a reference frame. The pendulum must be able to rotate about the z-axis as defined in the diagram. This rotational degree of freedom has been indicated in the diagram using a curved arrow. Another type of degree of freedom is the translational degree of freedom. While this type of motion is not present in the pendulum system, we will see a translational degree of freedom in the shock absorber assembly system in one of the following videos. These degrees of freedom are modeled using joints. Coordinate frames are used to define connection points between solids and are depicted in the diagram by the triad symbol or the symbol with the three arrows. In the diagram, the center of mass is represented by this symbol here. Finally, we will define how the solids are connected to one another, the location of the center of mass of each solid, the inertia, and how the solid geometry will be represented visually. Let's switch to MATLAB to see how we can model this simple system. Let's first clear our workspace variables by using the clear command. Then let's open up the Simulink library by clicking on this button here, and open a new model by clicking on this button here. Let's pull this to the right here. Now we will drag in a few blocks that will help us model our mechanical system. First, we will place the solver configuration block. Recall that this is a required block for all Simscape models. Refer to the Simscape introduction training video again to get more information about this. We can find this by scrolling down to find Simscape, and under Utilities, find the solver configuration block. Go ahead and drag this into your model. Next, we will drag in a world frame block. You can find this in the Sim Mechanics library. So under Simscape, go to Sim Mechanics. We have two options here, first and second generation. Second generation is the current modeling technique, so all the Sim Mechanics blocks we will be using will be from here. So let's go ahead and access that. And under Frames and Transforms, we can see the world frame block. Go ahead and add it to your model. This block establishes a reference frame for our mechanism and is fixed in space. Next, let's drag in a mechanism configuration block. This can be found under Utilities under Sim Mechanics. Let's go ahead and drag this block into our model. Let's double-click this block to set up its parameters. This block allows us to set the magnitude, direction, and units of the gravity for the mechanism. Without this block, the simulation will use a default gravity vector in the negative z direction. For our example, let's go ahead and change this so that the gravity is acting in the negative y direction. So our gravity vector will be 0, negative 9.8, and then 0. Let's go ahead and say OK to save changes. Next, let's go ahead and connect the three blocks. Before I do this, I'm going to select these two blocks and then use the shortcut Control R to rotate these blocks. And then I'm going to go ahead and connect these blocks together by clicking and dragging on these ports. Notice that when the blocks are connected, the lines appear green. This is because Simscape colors different domain connection lines with associated colors. This helps us identify and represent the different domains in a multi-domain model easily. The next step here is to model the pendulum solid. To do this, we will add a solid block. This can be found under the body elements library under SimMechanics. Let's go ahead and add the solid block into our model. Since this will be our pendulum link, double-click on the solid text here and rename this block to link. Connect the block directly to the world frame here. This means we are connecting the reference frame of the solid to the world frame. For solids created within SimMechanics, this is at the center of the geometry. To take a look at the geometry, double-click on the solid block to bring up its parameters. Here, we can set the geometry, inertia, and graphical properties of the solid. Note also the visualization in the block dialog to help us verify that the solid has been defined correctly. Let's go ahead and set the geometric properties first. We will leave the shape to brick because our pendulum link resembles a rod. Let's go ahead and change the dimensions for our brick. So in this case, let's set it for an example values of 4.5, 1, and 1 in the 3 dimensions, and set the units to centimeters. Note that when we change the dimensions, we have a message here to press F5 to update the visualization. We could do that or press the button here to update the visualization. The solid appears too small in our visualization window, so let's go ahead and click on this button to fit the model to view. Now we have set the geometric properties. Next, let's set the inertia properties. To do this, go ahead and access the inertia parameters. SimMechanics can automatically calculate inertia properties based on geometry and mass or density. For our example, let's set the density to 8,000 kilograms per meter cube. That resembles the steel material. Note here that we can also set the inertia to be a point mass. We will discuss more about these properties in later videos. Next, let's set the graphic properties. To do this, go ahead and access the graphics section of the parameters. There are several visualization options available. We will explore more of these in the later videos. For this example, let's go ahead and set the color here to blue. Select OK and update the visualization by clicking on this button here. Select OK to save changes. Now click inside the model and update the model by using the shortcut Ctrl D to bring up the Mechanics Explorer window. The Mechanics Explorer provides a 3D representation of a mechanical system. For example, let's switch this to the isometric view to see the 3D view. It also indicates the location and orientation of all the coordinate frames in the model. It includes a hierarchical tree view of the mechanism as well. We can use the animation view controls here to customize the view settings in the Mechanics Explorer. Specifically, the 2 buttons here can save and restore Explorer view configuration. This way, our view settings can be reused whenever the model is reopened and simulated. For our model, let's use the Y on top convention because our gravity is pointing downward in the Y-axis. To reflect this convention, click on one of the view buttons here again. Notice right now that the Z-axis is pointing upward. When we click on one of the views, now the Y-axis points upward, which is the view convention here. This visualization is useful when constructing a system, as we will be able to see a graphical representation, ensure that all frames are located and oriented as desired, and troubleshoot any issues that may arise. For example, currently the pendulum solid has one coordinate frame at its center of mass. However, the pendulum rotates about an axis positioned at one of its ends. To achieve this, we first need to create a frame at this location. We will do this using a rigid transform block. Let's go back to our model here. Let's drag in a rigid transform block from the Frames and Transforms library here. This block defines a new coordinate frame, which is the follower, relative to an existing frame, which is the base. Double-click the block to set its parameters. As we can see here, the rigid transform block can be used to both rotate and translate follower frames with respect to the base frames. In our example, the new coordinate frame is translated along the x-axis. To do this, let's access the translation part of the rigid transform. Let's set the method to standard axis and say translate along the x-axis. And the offset is half the length of the pendulum. So in this case, it's 4.5 over 2. And let's go ahead and set the units to centimeters. Let's select OK to save changes and connect the block between the world frame and the link here. Let's go ahead and update the model by using our shortcut Control D and go back to our Mechanics Explorer. Let's fit our model to view by clicking on this button here. Now we see a rigid transform has appeared. We can see two frames, one at the end of the link where we can define the rotational degree of freedom, and one at the solid's center of mass. The final step is to allow the pendulum to swing about its end. To do this, let's go back to the model. We can define degrees of freedom for our mechanical system using joint blocks in SimMechanics. For the pendulum, we need a single rotational degree of freedom, for which we will use a revolute joint. To do this, access the joints library. This library has several types of joints that can be used to implement different degrees of freedom for our model. Let's go ahead and add the revolute joint to our model. The orientation of the degree of freedom for the revolute joint block is about the z-axis of the two frames to which it is attached. The revolute joint block ensures that these two frames are co-located, in other words, the origins coincide, and that the z-axis of each of the frames are aligned. Let's double-click the block to take a look at its parameters. Blocks in the joints library also allow us to define internal mechanics such as stiffness and damping, set initial conditions, and configure physical signal ports for sensing and actuation. We will explore all of these options in later videos. So let's go ahead and select OK to save changes and connect the revolute joint between the world frame and the rigid transform block here. Let's go ahead and update the model by using Control D or shortcut and go back to the Mechanics Explorer. Here we see the revolute joint, and it is positioned at the end of the pendulum link. Now let's go ahead and simulate the model by clicking on the Run button here. We can zoom in and zoom out using the mouse scrolling wheel. We can replay the animation by clicking on the play button here. We can see the pendulum dynamics. The rod is rotating about the axis. Note also that it never slows down. This is because we have not incorporated real-world effects like damping yet. We also saw that the animation was very fast. This is expected because the dimensions of our pendulum were small. For a longer pendulum, the oscillations would be slower. In such scenarios, we can control the animation playback speed by using the controls here to slow down or speed up our animation. Apart from this, we have options for rotating, panning, and zooming our systems here. We can toggle the view for coordinate frames and center of masses of our mechanical system here. Finally, this option can create a video out of the animation here for later viewing, documentation, or reporting purposes. Let's go back to the presentation and do a small recap. We started with the Simscape solver configuration block that is required for all Simscape models, the world frame block that acts as a fixed reference for the mechanical system, and the mechanism configuration block that defines the gravity vector, magnitude, and direction. Then we added a solid block and created a simple brick and parameterized the length, width, and height. We also set the density value. The inertia of the solid was calculated from the geometry and density. Next, we talked about coordinate frames. In our case, we wanted to move the center of mass of the brick with respect to the world frame by half the length of the brick so that we can define the rotation about the pendulum's end and not the center of mass. We did this using the rigid transform block. We also noted that this block can be used to do both translation and rotation transforms. We will talk more about this in later videos. Next, we used joints to define the degrees of freedom for the pendulum. Particularly, we used a revolute joint for the single rotational degree of freedom. This defines a rotational motion about the z-axis for the base and follower frames. Finally, we simulated the model and inspected the result using the Mechanics Explorer window. We also talked about how we can control the visualization using the controls here, and the playback animation using the controls here. In summary, we talked about what SimMechanics is, the terminology used in multibody simulations such as solids, coordinate frames, joints, etc., and how to implement them in SimMechanics. Finally, we saw how to visualize the mechanical system. This concludes this video.